Let's now go through the proof of Mch4, rule 1, which is a really uninteresting sounding result, but we'll see in the context of everything that follows it becomes slightly more interesting. In other words, we're going to use it to derive some less trivial sounding results. But this one doesn't sound very exciting. Rule 1 says, if we're watching a meter stick moving by us with uniform velocity, it's just cruising through space in a direction perpendicular to its length. So here's its length. I'm watching it go by and it's moving in a direction perpendicular to its length. Then if I compare its length to an identical meter stick sitting at rest in front of me, I'll find that the lengths are the same. And of course, that's not so amazing. That's what we expect from our intuition. But again, we'll find out that, first of all, there are very similar sounding results that are not in agreement with our intuition in the theory of relativity, and that's what makes it so famous. So let's first pull apart. I'm going to do this in, I think, 2 different videos because it's going to take a little bit of time, so bear with me. Let's first talk about a couple of the terms that are in Rule 1, just to make sure we're all on the same page. Uniform velocity means that we're watching the stick going by. If it has uniform velocity, that means that all points on the stick are moving with the same velocity. In other words, it can't be true that the top is moving at 5 meters per second and the bottom is moving at 3 meters per second, which would cause it to start to rotate or something like that. So no, we're not talking about rotating meter sticks. We're not talking about accelerating meter sticks. We're talking about a constant velocity. The velocity is not changing with time, and it doesn't depend on where on the meter stick we're looking. It's just translating by in the most kind of boring way. Second term I wanted to talk about is direction perpendicular to its length. That means the length of the meter stick, we mean along the measurement direction. It's moving in a direction perpendicular. So this angle here is 90 degrees. In other words, this, if this meter stick had the same orientation but were moving up and to the right, we would not say that it's moving perpendicular to its length because this angle is not 90 degrees. Same thing here. This angle is slightly less than 90 degrees too. So we're talking about a case that looks like this. And the claim is when we measure its length as it's zooming by, we get no difference from the case where it's just sitting at rest in front of us. Okay. One thing I need to remind you of before we get into the proof is a technical point about the definition of an inertial reference frame. Here I'm sort of summarizing it as a coordinate system that happens to have clocks on it. It's an infinite 3-dimensional coordinate system made of meter sticks with clocks everywhere that moves uniformly, from which events can be viewed or measurements made. And in this case, so I'm picturing here 4, sort of an idealized picture of 4 different inertial reference frames. They're all moving with different velocities. But the point I wanted to make here is even if they were all moving with the same velocities, in other words, their velocity vectors were the same, if they have different orientations, and I'm showing the orientations by the orientations of the observers and the meter sticks here, if they have different orientations, we're going to call them different inertial reference frames. Okay, so that's the first statement here. So not only your velocity matters, but your orientation matters for being a different inertial reference frame. And therefore, the principle of relativity, which I abbreviate sometimes as PR, says that if we perform the same experiment in all 4 of these inertial reference frames, we should find that the observers in those frames obtain the same outcome. And we're going to use that in the proof that follows. So keep that in mind. All right, let's go on to, we're going to prove what I call claim 1 here in this video, and then we'll take a little break and go on to the later claims that gets us to rule 1. So claim 1 tells us something about the symmetry. If we call the 2 different sticks A and B. So here's a picture from A's point of view where A's stick is at rest and B is zooming by in the manner we have described. And here's a picture from B's point of view. In other words, the inertial reference frame in which B is rest and A is zooming by as time goes on. The claim 1 is about the required symmetry between these two views. In other words, if A and B are parallel and B is moving in the direction perpendicular to its length from A's point of view, then B is going to observe the same kind of motion. Parallel sticks, perpendicular motion of A's stick there. Okay? Now, in this case, we're not necessarily claiming anything about the lengths. Maybe the lengths aren't symmetric. In other words, from A's point of view, A's stick is longer and B is shorter, but from B's point of view, B's stick is longer and A's is shorter. Maybe. Who knows? We're not concerned about the lengths here. The symmetry I'm talking about is about the orientation of the sticks and the state of motion. Okay, so we're not going to allow them to not be parallel in the other one if it looks like this in A. They can't not be parallel in B, and they, even if they're parallel, they can't not be moving perpendicular to the length in B's situation if A looks like that. That's what the claim says. So let's write it down a little bit more carefully, because we're going to have to be careful in proving it, even though it seems like it should be intuitively true. So we're claiming if three things are true, if the principle of relativity is true, and sticks A and B are moving uniformly, and from A's inertial reference frame point of view, stick B moves perpendicular to stick A, and stick B is parallel to stick A. So I'm trying to draw that picture right here on the left. From A's point of view, this is what it looks like. Then the claim is, also from B's point of view, the first thing we're going to conclude is that stick A moves perpendicular to stick B. In other words, this direction of motion is perpendicular to B's length, and the two sticks are parallel there. Forget about the lengths. We're not claiming anything about the lengths here. It's about the orientation and direction of motion. How are we going to prove it? We're going to prove it in a little bit of a backward way. Sometimes this is called proof by contraposition. We're going to reason as follows. Let's just concern ourselves with conclusion 1 here. Let's show that in any imagined case where B and C are true, so B and C are the assumptions that the sticks are moving uniformly and that the sticks are perpendicular and the motion is perpendicular from, the sticks are parallel, the motion is perpendicular from A's point of view. If those are true, but conclusion 1 were not true, then the principle of relativity would be violated. And it takes a little bit of thought to wrap your head around this, but you can conclude from that. So in all cases where 1 is not true, the principle of relativity is violated. If the principle of relativity is true then, in addition to assumptions B and C, it must be the case that 1 follows. Okay? In all the cases where 1 is not true, the principle of relativity is violated. So if the principle of relativity is true, it must be the case that 1 follows. Okay, that's how we're going to proceed, by showing that the principle of relativity is violated if 1 were not true in addition to B and C. Okay, so let's set up a picture here. Because this is sort of convoluted logic, we're going to try to envision what's going on here. So here's stick A shown in red, and an observer in that reference frame that's at rest with respect to stick A. Here's stick B shown in blue and an observer at rest with respect to that stick. And we're showing this from IRF A. That means the one in which A is at rest. It's not moving. So from A's point of view, B and the stick are moving by to the right. Okay, so we're assuming if B and C are true, so sticks A and B are moving uniformly. I'm trying to draw that here. It's hard to draw uniform motion, but let's assume that goes with the picture. And the two sticks are parallel, and B's stick is moving perpendicular to the length of A. So that's what the assumption is here. But let's suppose that conclusion 1 is not true. Conclusion 1 says stick A moves perpendicular to B from B's point of view. So let's suppose that's not true. From B's IRF point of view, where stick B is at rest, B is watching A's stick go by. Let's suppose it's not moving perpendicular to the length of B's stick. Okay, so we're assuming that this is true, but we're assuming that conclusion 1 is not true, which is pictured over here, and we want to show that the principle of relativity would be violated in that case. Okay? How do we show that the principle of relativity is violated? Well, the principle of relativity talks about in two different inertial reference frames, if you perform the same experiment, the outcome has got to be exactly the same. Okay? So what we've got to do is find two different inertial reference frames in which the same experiment is being performed, but the outcome is different. That would mean the principle of relativity is being violated. For us, here's what one of our inertial reference frames we're going to use is. It's going to be the point of view of B. So what is B seeing? Here's what B sees. The outcome of the experiment is which way is this stick moving. Okay? The other reference frame that we're going to compare it to is one that's called B prime, which isn't shown yet in this picture. We need to construct it. So let's show what it is. It's not too hard to think about. Let's take some inertial, so A and B are inertial reference frames. Their orientation is shown by the little, human figures there. Let's consider two different, slightly different inertial reference frames. A prime is at rest with respect to A, but it's just oriented upside down. And similarly with B prime. B prime is at rest with respect to B, but it's just oriented upside down. Okay? And what I want to do is look at things from the point of view of A prime and B prime, and then we'll think about the principle of relativity. Okay? So here I have just looked at this picture over here with my head upside down and then drawn what I see down here. So here's A prime. Instead of having A prime's head upside down, we're going to show A prime's head right side up down here. What would A prime see? Well, nothing too different, right? If A sees the stick being straight up and down and B's stick parallel to A and going perpendicular to it, then A prime is going to see that same stick parallel to stick A and also moving perpendicular to stick A. Okay, so A prime sees the same thing as A if we disregard the orientation of the observers. The stick is oriented the same way and it's moving the same way. So A and A prime can have a conversation and say to each other, we see these sticks, B and B prime, and the corresponding observers, B and B prime, are moving in exactly the same way relative to us, and therefore they're performing the same experiment. Their experiment is a stick is moving towards us, and the outcome of the experiment is which way is the stick moving. Okay, so they're performing the same experiment. A and A prime can see that because A and A prime look at B and B prime and they say, hey, they're moving in exactly the same way relative to us. Everything looks identical other than the labels B and B prime, and so they're performing the same experiment. And therefore, according to the principle of relativity, they should see the same outcome. Now, we've already decided what B sees over here. We're assuming that if 1 is not true, if conclusion 1 is not true, then B will see stick A not moving perpendicular to B's stick. Okay? And now the question is, what does B prime see? In other words, if we look at this picture upside down and then try to draw it right side up, what do we see? It's not too hard to do. Look at it upside down and then draw what you see. Draw it right side up down here. Here's what B prime would see. That's a different inertial reference frame, B prime. B prime would see, don't worry about the orientation, we're not concerned about that, but if B sees stick A moving upward towards the top of his head as time goes on, then B prime would see stick A moving downward towards his feet as time goes on. Okay? And that is a violation of the principle of relativity. Again, A and A prime assured us that B and B prime were performing the same experiment because they look exactly the same. Every detail is the same there. But the outcome of the experiment is going to be which way is A's stick moving from B and B prime's perspective. And in this case, in one case, it's going up towards the head, and the other case, it's going down towards the feet. And that is a difference in the experiment. And therefore, the principle of relativity is violated. And therefore, because we've shown if B and C are true, but conclusion 1 is not true, then the principle of relativity is violated. If, in addition, the principle of relativity is true, then 1 has to follow. Okay? So that means that we have proved conclusion 1. A little bit convoluted, I know. It's called proof by contraposition, sort of doing it backwards that way. We're going to do a similar thing with conclusion 2. Now we want to conclude that sticks A and B are parallel from B's point of view. Okay? So let's do a similar kind of situation or a similar kind of approach. We're going to assume that 1 is true. We just showed that we should believe that 1 is true by the principle of relativity. So assume 1 is true. Assume assumptions A and B, again, that they move uniformly and that they're parallel and move perpendicular from A's point of view. But let's now assume that conclusion 2 is not true and show that there's a contradiction with the principle of relativity. And again, that will allow us to conclude that if all 3 of these are true and 1 is true, we already decided it's true, then 2 must be true. That's what we want to conclude. Okay, so let's set it up again. Again, this picture here first is just a picture of assumptions B and C being made into a picture. So from A's point of view, the 2 sticks are parallel and B's stick is moving perpendicular to A's stick. Here's the assumption that 2 is not true. It is not true that sticks A and B are parallel from B's point of view. So here's B observing the motion of A and saying, oh, wait a minute, our 2 sticks aren't parallel anymore. And again, we're going to show that it contradicts the principle of relativity by forming those same inertial reference frames, A prime and B prime, which are just upside down relative to A and B, but are moving in otherwise the same way. What is A prime going to see? Exactly the same thing that A sees, other than the labeling of B and B prime. It's a stick moving in exactly the same way toward A and A prime. So A and A prime get together and say, we see that sticks and observers B and B prime are moving in exactly the same way relative to us. Therefore, they are performing the same experiment, so they should see the same outcome if the principle of relativity is true. If they don't see the same outcome, then the principle of relativity is violated. So B and B prime are performing the same experiment. Let's see what B prime sees. Again, we just turn our head upside down over here and draw what we see right side up over here. When you do that, here's what B prime sees. And one way to characterize this is B says the outcome of the experiment is the side of the meter stick near my feet reaches me first, whereas B prime says the side of the meter stick near my head reaches me first. And those are different outcomes, and therefore the principle of relativity is violated. So, again, by contraposition, that means that if the principle of relativity is assumed to be true, 2 must also follow. The sticks have to be parallel. Okay? So this is the claim about the symmetry between A's view and B's view. Again, we're not concerned about the lengths of the sticks. We'll get to that in the next video. But what we've shown is if A sees something like this, then B sees something like this. Seems completely intuitively obvious, but we need to be careful about how we prove these things. We'll show that equally obvious results are not true later on. Okay, let me stop the video there, and we'll continue in the next video with 2 more proofs that allow us to prove Rule 1.